Good afternoon, everyone. First of all, thank you for being here today. Um, Today, I'll be presenting my dissertation utilizing full duplex multiple antenna in heterogeneous networks. This is not working. Just a second. Okay. Okay. This is not responding. Mm. It's not responding. Yeah, here we are. Okay. So the outline of the presentation. First, I will begin with an introduction of the dissertation. Then I will state the motivation and contribution. Afterwards, we will discuss the resource allocation challenges in full duplex MIMO heterogeneous networks and study the asymptotic rate analysis of the full duplex in massive MIMO networks. And finally, we will state the conclusion and the future work. Um with the introduction, I'm going to address three topics: the full duplex communication, the heterogeneous networks, and the massive MIMO networks. For the 5G, it's expected to have the 5G by 2020. So the 5G of mobile networks is expected to be released. But up to this point, we still haven't any standards for the 5G communication. But what are the challenges that are facing the full duplex communication? Uh, oh, I'm sorry. Okay. Yeah. So the challenges that are facing the full duplex communication is to the 5G communication is to increase the user rate and to increase the capacity. However, we need to decrease the cost and to decrease the latency. So our question now is to how to meet these challenges. So for that, we will address the first topic, which is the full duplex communication, which can potentially doubles the speed of the wireless communication. Also, we will address the heterogeneous networks, which can offer more spectrum and increase diversity. And finally, we will address the massive MIMO communication, which can offer significant gains in data rates and link reliability. For the starting with the full duplex communication, the idea of the full duplex communication is actually very simple, which to allow each communication node to transmit and receive on the same frequency and time resources. So this will help in having high spectral efficiency, uh, because instead of the time and frequency resource be designated for only transmission or only reception, now we can double this by having both on the same time and frequency resource. Also, this will be has low it will has low it will have low cost, because this can be implemented on the existing half duplex radios, on the existing half duplex system. But however, in order to realize or make the full duplex feasible, we should avoid the self-interference. As we can see, the self-interference is the interference from the transmission node on the same reception of the node. So, and actually, if we can compare between, this is the signal of interest, this small one, and the red one is the self-interference. Practically, the difference between the power of the signal of interest and the self interference is about 110 dB. So this is actually the received signal, which is just a summation of both signals. So when we come to the analog to digital converter, all the quantization level will be reserved for the self interference, so which will cause a saturation for the analog to digital converter. And that's why we say that the analog to digital converter is actually a bottleneck in the full duplex communication. For now, we have some works in the self-interference cancellation that has been done, which actually able to decrease the power of the self-interference to make the full duplex communication feasible. Um, the next topic we will talk about is the heterogeneous networks. The heterogeneous networks idea is to have the normal macro networks, but to add some small cell access point, which will differ in their coverage. So we can have pico or micro, we can have some fem to cell access points. This will actually help in increasing the capacity in hotspots if we have and some areas with high number of users. So we can by deploying these additional small cell access points, we can increase the capacity in these areas. Also, we can help in offloading from the large macro cell. However, this will actually complicate the network planning, how to where to put these access points, and also will increase the interference on the downlink reception, because now if there is a downlink transmission reception at the user equipment, there will be a lot of sources access points and that will be transmitting at the same time. So this will increase the interference of the downlink reception. Finally, we have the idea of the massive MIMO networks. And the idea of the massive MIMO networks is to have hundreds of antennas deployed at the base station to serve a small number of users. So now we're not talking about 4x4 transmission or 2x2, it's like hundreds of antennas. So this will help us uh, in having lower transmission power, because in that case we have high antenna gain, and this antenna gain will allow us to decrease the transmission power. Also, from the main advantages of the massive MIMO is to have the channel hardening. The channel hardening is simply by increasing the number of antennas, so that the total channel gain randomness will decrease. So the randomness will decrease, and the main gain will depend on the number of antennas we are using. Also, we will have accurate spatial multiplexing, which also a result of having large number of antennas. As the number of antennas increases, the accuracy of the spatial multiplexing will be better. However, increasing the number of antennas has some challenges. First of all is the antenna correlation. In order to have two channels from two antennas to be independent, we should have some separation between the antennas. So when we are now talking about large number of antennas to be stacked at the base station, we may not be able to keep this distance separation to have uncorrelated channels. So maybe we will have some antenna correlation. Also, with the problem with the massive MIMO, or a challenge in the massive MIMO, is to acquire the channel state information, because now the number of channels needed to be estimated is very large, and we need the orthogonal pilots, which will lead us to the third problem, which is the pilot contamination. The pilot contamination is actually in the channel estimation part, we need to use orthogonal pilots, but as the number of these channels needed to be estimated increases, we need to have more orthogonal pilots, and the number of orthogonal pilots is limited. So in that case, we will have to reuse the pilots. In that case, for example, if we have this user is trying to, the base station is trying to estimate the channel from user 2, both user 2 and user 1 in a neighboring cell use the same pilot. So the channel estimation at the second base station will be corrupted by this pilot transmission from a neighboring cell. So we have the pilot contamination in the channel estimation. From these three techniques, we can now state our motivation and contribution of this dissertation. So our motivation is to answer the following question. The first question is, what are the benefits and the challenges of combining full duplex and massive MIMO in the heterogeneous networks? Also, we want to know when to utilize the full duplex communication. What is the asymptotic full duplex rate behavior? And in order to answer these questions, we investigate the performance key in full duplex MIMO heterogeneous networks. We propose mode selection criterions between full duplex and half duplex. Also, we jointly optimize the user pairing and subcarrier allocation in full duplex OFDMA networks. We propose the crystallized rate region to derive the full duplex rate region with lower complexity. We derive the full duplex downlink and the full duplex uplink asymptotic rate bounds, and we optimize the self-interference cancellation in full duplex massive MIMO setting. The next step is to discuss the resource allocation challenges in the full duplex MIMO heterogeneous networks. The outline of this chapter is first to study the performance keys in the full duplex MIMO heterogeneous networks, then and study the resource allocation problems, and finally to propose some solution algorithms. At this figure, we are considering a two full duplex nodes with a downlink user and an uplink user, an uplink user, multiple downlink and uplink. So if we have a look on the downlink transmission, um, on the uplink transmission, the main challenge on the uplink transmission is the high value of the self interference. Because so in that case we will need a downlink power control. Why do we need a downlink power control? Because the self interference is actually initiated from the downlink transmission. So this is the first resource allocation challenge we need to do. Also, the second problem is the co-channel interference. What do we mean by the co-channel interference? The co-channel interference, if we take a look on the downlink reception, so this is the received signal, and this is the received signal, and of course there will be multi-user interference from from other downlink transmissions, but there also as a result of having an uplink transmission, this uplink transmission will act as an interference on the downlink reception, and that's what we call the co-channel interference. So in order to decrease the co-channel interference, we will either make uplink power control, we will need uplink power control to control the power of the uplink transmission, or to make the user pairing. What do we mean by user pairing? The user pairing, if, for example, if we are working on an OFDMA network, so to choose a downlink and uplink pair whose co-channel, where the co-channel interference between these two pairs is minimum. So in that case, we will decrease the interference on the downlink transmission. Then the next point we want to take into account is the multi-user interference, and this is a common problem between the half duplex and full duplex. And in that case, we will need, for example, if we're working for an OFDMA network, we will need, in that case, subcarrier allocation. However, if we are working additionally, if we are working in a MIMO network, the additional antennas will actually raise the need to know the number of transmission and receive antennas, because in the case of the half duplex, all the base station antennas are either for transmission or either for reception. But if we are working on full duplex, we need to know the number of transmission and receive antenna, and also the pattern of the transmit and receive antennas. So in that case, we need the antenna selection. Also, we need to control the self-interference, because as the number of antennas increases, the analog cancellation circuit may be very complicated to be implemented. So in that case, we will need self-interference cancellation with beamforming. So to sum up the resource allocation challenges we need to cover for the full duplex transmission without any MIMO, we will need the mode selection to switch between full duplex and half duplex. Also, we need the power allocation, whether in the uplink or the downlink. Also, we need subcarrier allocation if you are working in an OFDMA network, and we need the user pairing to decrease the co-channel interference. If we are working in a MIMO transmission, additionally to these four resource allocation challenges, we will also need the antenna selection and the self-interference cancellation with beamforming. These problems jointly will be mixed integer nonlinear programming. Why is that? Because the mode selection has a combinatorial nature. Also, the subcarrier allocation, the user pairing, the antenna selection, all of these are combinatorial problems. So, and while the power the power allocation is a continuous the power is continuous variables, so the joint optimization will finally be a mixed integer nonlinear programming. Okay, so now we will have a system to work on to address the joint problem. So we have a single base station. The base station is working on an OFDMA. So in each subcarrier will be serving one uplink and one downlink user. So if we take a look on the downlink transmission, the received signal will be the downlink transmission power, the large scale fading, the small scale fading, and then the noise plus interference will be the noise variance and the co-channel interference. The co-channel interference is, as I mentioned, the interference from the uplink transmission on the downlink reception. But how can we calculate the co-channel interference? The co-channel interference is given by the uplink transmission power, and the large scale fading is dependent on the uplink and downlink mutual distance. And finally, the small scale fading, which depends on the channel gain between the uplink and downlink pair. Similarly, we can study the uplink transmission, and in that case, the uplink transmission, the received signal will be the uplink transmission power, also the large scale fading, the small scale fading, and the noise plus interference will be the noise variance. And this value is the self interference, which is simply the downlink power over the self interference cancellation parameter, which is introduced from the full duplex radio already implemented in the base station. From these received SI and Rs, we can derive the capacity of the uplink and downlink, and of course the total rate. So the problem we need to solve right now is to maximize the total rate or the sum rate of the network in terms of the downlink powers, while keeping the downlink power constraints. Also, we want to optimize the uplink power, keeping the uplink power constraints, and finally to find the proper subcarrier allocation and user pairing. Here, this constraint is to guarantee that each subcarrier will only serve one uplink and one downlink users. And these are the binary assignment variables, which are binary coefficients. If this binary coefficient equal 1, then the n uplink is paired with the m downlink on the s subcarrier. So as I have mentioned, because we have these two are continuous variables, but these a are binary, so it's a mixed integer nonlinear programming. So we will need the generalized Bender's decomposition to solve this type of problem. A quick overview on the generalized Bender decomposition. The main problem that the generalized Bender's decomposition solve is to minimize the function f of x and y in terms of x, which is some continuous variables, and y, which are some integer variables. The main idea or the main steps of the generalized Bender's decomposition first is to initialize an upper bound and lower bound, and at each iteration we check if the lower bound is greater than the upper bound. If this condition is satisfied, then we reach an optimal solution, or initially the problem is infeasible. The next step is to solve or to formulate the primal problem. The primal problem is simply to solve the initial problem in terms of x, which is the continuous variables, but setting the integer variables at a constant feasible point, keeping the constraint on the integer values. After solving the formulating and the primal point, we check if the primal problem is feasible. If the primal problem is feasible, we will update the upper bound, add an optimality cut. I will explain in a second what is the optimality cut, and formulate the relaxed master problem. What is the relaxed master problem? The relaxed master problem is to minimize y node, to find the minimum y node, subject to this value to be greater than y node for a certain number of iterations. So this kf is the number of feasible iterations. So each time I check if the primal problem is feasible. If the primal problem is feasible, so I increase the number of feasible iterations, and in that case I will have one more optimality cut, and it's given by this value. So the L to power star is given the Lagrangian of actually it's the Lagrangian of the primal problem. However, if the primal problem is not feasible, so I will have a certain number of unfeasible iterations, and in that case the L sub star will be given by this formula, which is actually the Lagrangian of the feasibility problem given by this formula. After solving the relaxed master problem, I update the lower bound, and each time I check the iterations, and the iteration continues till reaching the optimal solution. Another way to solve this type of problems is to have a heuristic algorithm. So in that case, we will propose a two-step iterative algorithm to solve this joint mixed integer nonlinear programming. The first step is to solve the combinatorial part, which is the user pairing and the subcarrier allocation. And using this solution, then we can solve the power allocation problem. So let's start with the first part, which is the joint user pairing and subcarrier allocation. The main idea is to first to construct an initial candidate triplet. What do you mean by triplet? The uplink and downlink and the subcarrier. So the phi initial or the initial candidate set is mainly the uplink user, downlink user, and subcarrier, which belong to the downlink user sets, the uplink user set, and the subcarrier set. These three triplets must satisfy this condition. What is this condition? That the co-channel interference between these two pairs on that subcarrier must be over the variance must be less than the SNR wall. The SNR wall is the least detectable SNR by the user equipment. So if if the transmission from the uplink on the downlink cannot be detected by the downlink, so that's mean that we have minimum co-channel interference. So after constructing this initial candidate triplet, we can, for each subcarrier, we can choose the highest uplink and downlink pair, the highest sum rate uplink downlink pair. After getting the solution of this combinatorial part from this algorithm, we can go forward and solve the power allocation. But before solving the power allocation, we should mention that this algorithm has a complexity order of in the order of s n squared all to power 2. S is the number of subcarriers, n is the number of users. So this is a quadratic complexity. However, the full search algorithm, which is to enumerate all the possible cases, will have an exponential complexity n2 to the power 2s. So if we can compare, we can see that we decreased the complexity of solving this combinatorial part. The next step, as I mentioned, is the power allocation. For the power allocation, it's expected that it will be only in the terms of the uplink and downlink power, because we have already solved the combinatorial part. So it will be to maximize the total rate in terms of the downlink powers, keeping the downlink power constraint, and the uplink power, keeping the uplink power constraint. For the highest SI in our case, we can prove that the power allocation problem is a convex optimization problem, and in that case, we can use the ADMM for solving this type of problem. The ADMM basically is to solve a problem in this form, which is a sum of f of x plus g of x, where f of x and g of x are convex problems. The algorithm of solving these problem using the ADMM is done by 3 steps. The first step is the x update. The x update is mainly concerned by f of x. So and the next step, so the x update is is dealing with f of x, and the proximal operator is to minimize f of x plus 1 over 2 lambda x minus mu all square. The next step is to do the z update. Z update is actually it's similar to the x update, but it's now working on the g of x. So the first step is to have this reformulated as f of x plus g of z, and then work on the x update on f of x, and work on the update on g of x. And finally, we will have some dual variables to I'm sorry we will have some dual variables, this u, to check the difference between the x and z, and this actually will determine the stopping criterion of the ADMM solution. In our problem, we will need the main advantage of the ADMM, which that it can solve separable problems in a distributed way. Solving any problem in a distributed way actually is very important in decreasing the complexity of the solution. So if we have a problem in the form of it's as a summation of objective function, so this is a separable objective. It can be separated over the variables of optimization, subject to some constraint. This actually can be reformulated as an indicator function on the allocation set. So this I is an indicator function. The indicator function is 0 when these variables are within the allocation set C, and infinity if these are not satisfying the constraint. After reformulating the problem in that formula, we can then derive the ADMM algorithm. So the first step is the same as we discussed before. However, the second step now becomes a projection on the allocation set. The projection is the same as the proximal operator when applied on an indicator function. It's the same as the projection on this complex on this allocation set. And finally, the last step is to measure the difference between the x and z. After solving the problem using this heuristic algorithm, so the algorithm is to solve this combinatorial part and then the power allocation and then reiterate till reaching the solution. So we need to compare the results we have proposed between this algorithm and the optimal one. So first we will study the mode selection criterion. The mode selection is to allow the system to switch between full duplex and half duplex. So if this is the half duplex transmission, the downlink rate of the half duplex of the full duplex transmission, and this is the half duplex transmission, we can see that on average the switching between full duplex and half duplex will have a better gain. Also, if we have this here, we are changing the self-interference cancellation. So the half duplex is not affected because we don't have any self-interference in the half duplex. But the full duplex, as the self-interference cancellation increases, the downlink increases as well. The sum rate is increasing. So the switching criterion will always follow the higher. So on average, we will have some gain. So to conclude from these two figures, we can have high gain at low spatial correlation. This part has higher gain than this part, and also we at large self-interference cancellation, we have high gain by the mode selection. So in the next figure, we are comparing between the exact solution we have obtained, which is the solid line, and these diamond line are the proposed algorithm for a certain value of downlink power. And here we recompare at the different power of downlink. So also these diamond parts is the proposed algorithms, and these dotted is the exhaustive. So from this figure, we conclude that difference between the exact solution and the proposed algorithm is very small. This comparison is done at small numbers of subcarrier and user. For a higher number of user and subcarrier, instead of comparing with the exact solution, we compare with the upper bound obtained from solving the dual problem. So this is the dotted line is the dual problem, and this is our proposed algorithm. And also the difference is very small for different scenarios. So this for 48 antenna subcarriers, and this is for 16 subcarriers. So we can conclude that the difference between the upper bound and the proposed algorithm is also small. This figure is comparing the sum rate of our proposed algorithm, the random allocation, if we just randomly allocate users to subcarriers, and finally the half duplex. And we can see that we have better performance than the random allocation and the half duplex, which is expected. The next step is another way to compare between the full duplex and half duplex is to derive the rate region. The rate region, the idea is to have two rates of the networks, which are, if this rate increase, so this is expected to be decreasing. So they are not always increasing together or decreasing together. So we have one increasing and one decreasing. And idea is the full, which we call the full search rate region, is we fix, for example, R1 at a certain value, and to maximize the rate R2 and drive and have a point on the rate region, and then we swipe the fixed value over all possible values of R1, and in each time we have a point on the rate region, and we finally construct the rate region. This method is called the full search rate region, and we should consider all cases of users and power allocation, which is, of course, maybe a very complex process. Instead of having the full search rate region, we are proposing crystallized rate region, which will consider only a subset of combinations which most likely lie on the boundary of the feasible rate regions. For example, we know that this point is that in that point at the corners, one rate is equal to 0. So we know that this will lie on the boundary. After considering some set of points that we think that will lie on the boundary of on the feasible region, we will construct the convex hull based on those combinations. For this idea, we work on a network with two nodes, node N and node M. So if we want to increase the sum rate of node N, we will need to increase the uplink and downlink of the downlink power of node N and the uplink powers of the users connected to the node N. But this will actually increase the interference on the downlink and uplink reception of the at the M based node and the users connected to the M node. So here the what I've mentioned before, that I have one to increase one, the other will be decreasing. The question now is to know what are the set of points we need to consider. So the first set of points is to consider either node N or M is silent, which are the corner points of the rate region. The first node N is silent, along with its all user are silent, so we can maximize the rate of the other node. Or alternatively, the second node is silent, and the other one we need to maximize its performance. So this is the first set of points. The second set of points is to assume that either node N or M transmit at the maximum power. And the third set of points is only downlink is active, and in that case, either one of the two nodes downlink is active, or both nodes are active. And similarly, we have the only uplink is active, which also can be divided into three cases. Node 1 is downlink is active, or node 2, or both nodes. After solving these rate maximization problems for these points, we finally construct the convex hull. The idea is simple, but we need to verify or validate its performance. In order to do so, we'll study the system for different interference conditions. So for a high interference condition, so we have this solid line is the full search region, and the dotted one is the crystallized for the full duplex transmission. And this red one is for the half duplex transmission, the full search, and this one, the dotted one, is the crystallized for the half duplex. And as we can see in the case of the high interference, the crystallized region can fully include the full search region. So in that case, sometimes the time sharing between these 2 points may be more beneficial to have higher rate than the power adaptation region. The next step to validate the performance is to study the interference in the case of low interference transmission. And in that case, this solid line is the full search region for the full duplex, and this is the crystallized for the full duplex, and those for the half duplex. In the case of the low interference, we can see that the crystallized, which is the dotted one, offers a very good approximation to the full search region. The loss in the rate, so the time sharing between these 2 points can achieve very close rates to the one achieved by the power adaptation of the full search region. So by these two figures, we can validate the performance in different interference conditions. The next step is to study the asymptotic rate behavior in the full duplex MIMO. The asymptotic rate behavior, we mean how the rate will change when the number of antennas grows to infinity. The outline of this chapter is first to study the random metric theory, which is the tool we need to drive the asymptotic rate. And then we will see how the rate will behave when the number of antennas grows. And finally, we will see or study how to optimize the performance of the full duplex massive MIMO networks. The random metric theory studied how the vectors will change if its dimension grows to infinity. So if we are studying two vectors P has n entries and Q has n entries, be mutually independent n times 1 random vectors. The entries of P and Q are IID, zero mean random variables. The expectation of each entry in P square equals sigma P square, and the expectation of each entry of QI square equals sigma Q square. And So if we have to calculate, if you want to calculate this amount, 1 over n p Hermitian p as n tends to infinity, so the dimension n tends to infinity, this will tend to sigma p square. And if we want to calculate the 1 over n p Hermitian q as n tends to infinity, since these are mutually independent, so this value will tend to 0. Another theorem we want to use in our study, that if we have A is an m by n random matrix whose columns are zero mean independent complex Gaussian vectors, if we construct for n greater than m, construct a matrix B, which is equal A Hermitian, so B is called a central complex Wishart matrix, and the expectation of the trace of B inverse will be dependent on the dimension of B, which is equals m over n minus m. Finally, if M is a m by n random matrix whose columns are also a zero mean independent complex Gaussian vectors with identity covariance, so the value of 1 over m B Hermitian B will tend to identity identity matrix as n tends to infinity. Using these three facts, we can calculate in this network, we can calculate the upper bound of the downlink full duplex transmission. So the upper bound of the downlink full duplex transmission will be dependent on the number of downlink users, the number of transmission antennas, the number of receive antennas, the downlink SNR, which is simply the ratio between the downlink power over sigma square, and this value sigma psi of lambda nu, and lambda nu is sigma square over pu, and the value of lambda mu is also dependent on the number of uplink users, number of downlink users. So we can see from this formula that the upper bound of the downlink capacity is now not dependent on there is no randomness in this value. It's depending on the number of antennas and the number of users. And this is what I have mentioned in the beginning of my presentation, that the massive MIMO make the capacities or the randomness in the transmission decreases. Similarly, we can derive the lower bound for the uplink full duplex and for the half duplex as well, the upper bound and lower bound for the downlink and uplink for half duplex. Based on these bounds, we can decide when the full duplex is better. So if we want the downlink full duplex to be better than the downlink half duplex, we should keep the transmission antenna greater than this value and the receive antenna smaller than this value, and finally the expected value of the co-channel interference must be less than this value. If we keep these three conditions satisfied, then we can state when to have the uplink full duplex better than the uplink half duplex. The uplink transmission is mainly affected by the self-interference cancellation parameter, so in that case our condition will be on the self-interference cancellation, and it will be dependent on also the number of receive antennas, the number of transmission antennas, and so on. So in that figure we are validating the bounds we have derived. So this is the solid line is the simulation, the downlink capacity from the simulation, and the dotted one is the bound, and similarly this dotted one is the lower bound, and the diamond is the simulation. So as we can see that the derived bounds are tight. Then the next figure we validate the number of transmission antenna threshold and the co-channel interference threshold. So this is the half duplex transmission, and this is and the x-axis is we are increasing the number of transmission antennas and check whether the downlink full duplex is better or not. So for these two cases, the co-channel interference is small, and in that case we can find a value of transmission antenna after which the full duplex is better. However, in this figure, the co-channel interference is very high, so if we increase the number of antennas to be n, which is the total number of antennas, we still have the downlink full duplex less than the downlink half duplex. So we can conclude that for large co-channel interference, the full duplex down rate is always less than the half duplex down rate, however how much we increase the transmission antennas. So up to this point, we didn't make any performance optimization in the full duplex massive MIMO network. So The next step is to try to optimize the self-interference cancellation, because as I have mentioned, the self-interference in the case of the MIMO networks, we need to do some self-interference cancellation with beamforming. So in that case, we will design the downlink transmit precoder to cancel self-interference on proportion alpha of the receive antennas, where alpha is from 0 to 1. If alpha equals 0, then there is no SI cancellation with beamforming, and if alpha equal 1, so we cancel all the self-interference on all the receive antennas. Based on this, we will construct like an aggregated channel matrix, which is constructed from the downlink channel matrix and the channel matrix between the transmit antennas and the alpha NR receive antenna at which we want to cancel the self-interference at. So as we can see from the figure here, this is alpha NR and this is HA, this one. So we will cancel the interference on these alpha NR. Using this aggregated channel, we construct the zero forcing precoding matrix, and then we just here this just a normalization coefficient. So the lower bounds of the full duplex rate is given by in terms of beta, which is the antenna ratio, and alpha, which is the ratio of the RX antennas at which the self interference is cancelled, will be dependent on the number of downlink users, the downlink power, the uplink power, and the uplink users, and of course some dependence on beta and alpha. And similarly, the lower bound of the total full duplex uplink rate will depend on beta and alpha, but will also depend on the self-interference cancellation. Based on these two capacitors, we can maximize the rate region by two ways. The first way, is to choose a constant value to the uplink capacity and try to maximize the downlink capacity. The other way, alternatively, we can choose a constant value for the downlink capacity, but to maximize the uplink capacity in terms of beta and alpha. So we're going to formulate these two problems and compare between the two solutions. If we maximize the uplink lower bound we have derived, we can obtain a relation between beta and alpha. This relation is a linear relation. However, in that case, if we set a constant value for CD, we can obtain another relation between beta and alpha, which is a nonlinear relation. The next step is to substitute in the formulas derived before beta in terms of alpha, so the problem will be all in terms of alpha. So the problem, the rate maximization problem, is to maximize the uplink in terms of alpha, where alpha from 0 to 1, and the other will be the same here, but to maximize the downlink capacity, not the uplink as here. This problem can be proved to be a convex optimization problem, and we can obtain a solution for this problem. So the uplink power will be maximized, the uplink capacity will be maximized at alpha equal 1, which is expected because at alpha equal 1, so we mean that we cancel all the self interference on all the receive antenna, and that's expecting to be maximizing the uplink capacity, and the value of beta can be obtained from the relation we have derived before. On the other hand, this problem is not a convex optimization problem, so alternatively, we will solve its dual solution, the dual problem, and we can obtain that the solution of the dual problem will be at alpha equals 0, and lambda 1 and lambda 2 are the dual problem. Lagrange multipliers will be equal 0. So the next step is to...
Is that a typo, or did you iterate? Because here you say constant CU.
Yeah, so this step is we set the value of CU at a constant value, and then we maximize the downlink. And in each time we change the constant value of CU and obtain the solution by this.
Okay, therefore this is the iteration. It is not that you're maximizing CD here. You maximize CD and now you're changing CU.
So we know that the maximum down, so that we change this CD from 0 to its maximum value. The maximum value is when all the antennas are transmission antennas and there is no cancellation. So this is the maximum value of the CD. So we change this value of CD from 0 to its maximum value, and at each point we maximize the CU. So actually alpha will always be 1, but beta will always change. And similarly here in that case. In this figure, we validate that the downlink capacity is minimum at alpha equals 1, okay, for different values of the constant CU, and this figure shows different rate regions. This one is the half duplex rate region, the solid one, and the dotted red one is the full duplex obtained from the solution of maximum of the dual problem, the solution, the simulation and the optimization, and the solution we've proposed. And this one is the result from the convex optimization problem, also the simulation and the algorithm and the solution we proposed. And this one is actually the system when no self-interference cancellation is to maximize the rate region when no self-interference cancellation is considered, so alpha equals 0. And in that case, it was found that the optimal antenna ratio is the number of downlink users over the uplink users. So from that figure, we can validate that in a full duplex massive MIMO network, we should consider the self-interference cancellation in the beam forming in order to have a better rate region than maximizing the rate region with no self-interference consideration. So in conclusion, we investigate the resource allocation challenges in full duplex MIMO heterogeneous networks. We proposed a heuristic algorithm for user pairing based on defining the user equipment SNR wall. We derived the full duplex operation region for different network scenarios. And finally, we optimize the self-interference cancellation in a full duplex massive MIMO setting. In the future work, we will study the antenna selection problem in the full duplex MIMO network, how to choose these patterns, how to know the numbers, which arrangement of the antennas will give better performance, and to study the beamforming optimization in full duplex MIMO networks. Because before we assumed that we have a zero forcing precoder, now we can study how these weights should be optimized rather than the zero forcing precoder. And finally, we'll study the effects of the pilot contamination, how it will affect self-interference cancellation via beamforming. This is the last list of references. And any questions?
Question?
I'm the most junior one, so I can ask a question. Could you go to page number 18?
18, okay. Okay.
That's number 18? Okay.
Yeah, here it
Could
is.
you please one more? Like standard conversation?
Yeah, that's on the,
Yeah, because you said there's a mixing integer nonlinear program.
yeah. Yeah.
We all know that if we use standard computation, we can generally solve mixing integer linear programming.
Mm-hmm.
But I don't know, can we use standard computation to resolve
Yeah, and yeah.
nonlinear one, or is there any part you convert the nonlinear programming into linear one?
Yeah, as I have mentioned, so the first part will be not unchangeable, which is the setting the primal problem, and so the first part, yeah, there's this part. So this will be actually a nonlinear programming. It's a nonlinear problem. The primal problem will be a nonlinear one, and there are actually some algorithms that have been there to solve these type of problems.
So I think this study just relies on final value into continuous one, right?
No, we set the integer values at a constant value, so they are no longer there. So we are just optimizing in terms of the continuous variables. So we set as constant value y bar.
Could you go back to the formulation? Let me check where the nonlinear part. Original formulation on number 18. Page number 18.
Okay.
So the nonlinear part comes from.
So it comes from here, from the actual sum rate.
Okay. If you see, so I believe we can work on one, so okay. But generally speaking.
Yeah, for convex, not a problem. For non-convex, for convex and linear is the same story. But here, okay, for this, they only work on the high algorithm, so that they can be a kind of convex, and also it can be solved by ADN. Otherwise, you can only solve the field problem, which is a kind of always convex, but you have duality there.
So could you go to page 25?
Should be easier.
So
25.
it's about the ADM.
Sorry. Lots of animation.
Okay. Yeah, you can stop here. It's fine. I think I can understand why you want to use ADMM because if there are too many users, too many antennas, this problem is supposed to be a very complex problem. So if you use ADMM, it can help you to solve it in a distributed way. I just wonder, but as you mentioned, in your networking setup, who is going to do the local calculation, do the local updates?
So let me go back.
I mean, in your general scenario, there's a very big base station over there with many antennas, MIMO antennas, whatever. Then there are a bunch of users. So you're going to distribute the computation task into the user.
Yeah. So the only the uplink user equipment. So the downlink is automatically in the base station. The power allocation of the downlink will be in the base station, but the uplink users will compute these local uplink powers.
Okay. So the only advantage is from the computation part, nothing from the general networking, setup.
Yeah.
And I think I know a little bit. For other power control, typically Dr. Rory is writer kind of framework for that standard function, but that is not applicable here. In the sense that the problem becomes much more complicated. You could hardly have this kind of ADMA power control, the standard function conversion. You look like a converter.
Now, you mentioned at the beginning heterogeneous networks, but I didn't see much discussion on that. Mostly about small cell network.
Yeah.
Okay. Yeah, go ahead.
Yeah. So when we were talking about these two nodes, this was a part of the heterogeneous networks, and actually I just picked some bits and pieces from the dissertation.
Therefore, your concept of heterogeneous, it sounded like you're going to look at femtocells or different kind of major cell and femtocell. And then, but throughout your talk, you only focused on sort of some users and their base stations, therefore small cells without femtocells.
So the crystallized region, I had the idea of the crystallized region is applicable on multiple nodes because if we go back, let me go back to the slide.
You don't have to go back. I remember.
Yeah, it was two nodes. So these two nodes could be one base station and one access point. And also I have some work that was in the dissertation with multiple a basic base station and some small cell access points. And we will try to solve this joint problem with larger number of smaller cell access points.
Now, in your again, you early on you talked a lot about massive MIMO, and then you immediately went to a regular MIMO as opposed to massive MIMO. And then you look at the asymptotic case when the number of nodes go to infinity, so that you could use a random matrix theory, right?
Yeah.
But then, did you have some results that sort of talks about large but finite number of nodes? I didn't see much about the total number of nodes and the impact of the total number of nodes. No, total number of
antennas. Yeah. So the performance of the it theoretically should tend to infinity. So let me show you the figure. Yeah. So this figure is actually for a finite number of antennas. It's not for to solve these problems. We work on like 60 or 70 total number of antennas
at the base station.
At the base station, yeah. And the next figure, the one I'm comparing the thresholds. The number of transmission antennas is from 50 to 300. So we should have it large, but large number of antennas, but of course theoretically is to infinity, and the approximation would be better as the number of antennas increases.
Now, one other question: you talked about massive MIMO at duplex and heterogeneous network or I guess small set network, right? And these sound like three could be possibly independent networking ideas, right? And then in a way you put them together, right? Now, was this? I was looking for some answers that say that the gain of the sum is bigger than the sum of the gain. The gain of the sum
is bigger
than the sum of the gain. Is that true?
Yeah, so you mean if we, let me just rephrase this question.
Please do, yes.
Yeah, so what I need me to tell you that if we use the full duplex alone and the small cell alone and the massive MIMO alone, it will not give the same as if we combine all together.
Is that, yeah. In other words, was there any sort of leveraging from one to another that helped you so that the combination system was performing, giving you bigger gain than the individual? Yeah, exactly. I'm rephrasing, you will rephrase it.
Yeah, okay. So let's take an instance of the full duplex communication. The full duplex communication is supposed to be for small coverage. So by using the massive MIMO, we can extend the coverage of the full duplex communication. So this is a point that we can make use of the combination of both. Also, if we are talking about the heterogeneous networks are supposed to be with a small power. So this small power will not enough. Only doing the small cell networks would be not enough to have these high performance gain we need for the next generation. So it will need something like the massive MIMO to boost the performance more. So each technique individually will not be able to meet the requirements we need for the 5G, for example. So that's why we need to combine more than one technique to have this high gain.
Were you able to quantify that?
Maybe this would be a good point to. Yeah. So we need to. Yeah. Okay. So.
You don't need to. It would be nice to.
Yeah. Okay.
And allow me to answer your first question and this question in another way. Okay. For heterogeneous network, after the duplex and MIMO, can be seen in this way. Okay. For HeatNet, you have a macro cell or small cell, but typically if you apply this full duplex or half duplex, full duplex typically is for small cell because of self-interference. So big macro cell, full duplex probably not work in the sense of self-interference, but this is how it's big. So basically, okay, depending on the cell size, depending on the interference, self-interference case, so for heterogeneous network, for full duplex, half duplex, there's a cut. That is where you should do full duplex, where you should do half duplex. And when it's multiple antenna there, then this cut will change. And then, okay, with more antenna, okay, maybe the cut will become better. But asymptotic case, what is the behavior? And he showed that, okay, I mean, for asymptotic, it will improve, but if your self-interference is too bad, it's not good enough. But you have a curve to see where this cut looks like. So basically, this means the heterogeneous network, multiplex, and the MIMO together. China, he told you first of all.
I have one more question. Yeah. Now, I mean, we saw a lot of results, right? And then I remember from your proposal exam, you also had a lot. Were there any results that you presented that was surprising to you?
Surprising to me. Let me think.
And then I'll tell you which one was most surprising to me.
So you can start first.
I already defended my thesis. But good answer though.
So to be honest, okay, this this threshold, this is the one who surprised me. To have the expected value of the full channel interference to be less than the noise, 3 times the noise power, which is actually, I'm supposing that this is very low threshold to have the downlink full duplex better than the downlink half duplex.
So do you expect that threshold to be higher? And then when you saw it to be just 3 times?
Yeah, I expect to have more space for the co-channel interference because there are too many users, so it's expected to have the co-channel interference to be higher than that. So this is actually a very small threshold to have the downlink full duplex better than the downlink half duplex. But actually, I think this study is done with no optimization whatsoever on the full duplex. We just drive the bounds and see when the downlink or when the full duplex will be better. So expectingly by optimizing further the full duplex communication, this should be better. It would allow for more co-channel interference. So what was your surprise?
Actually, my surprise was the figure that we were looking at.
Yeah. Okay. Let me go back to it.
No. Yes.
Yeah. Okay.
I was surprised.
Why?
I didn't think that he was going to take 200. I cannot even.
Yeah, it's about
250 antennas to bypass half duplex.
Yeah, and yeah, this is actually also the result from the bounds I have derived. So yeah, it needs a lot of transmission antennas, but this is with no optimization. So I guess with optimization to be much more better. We need less and less number.
By optimization, you mean again going back to alphas and betas and all that?
Yeah.
Okay.
Yeah.
Do you have this result for optimized alphas and betas? Because you did lay down optimized alphas and betas.
Yeah, but I didn't drive like this same result. I was just I have actually compared only the rate region, but after optimization I compared the rate region. So let me show you.
That's not the same, right?
Yeah, this is not the same, of course, yeah, but we can see that the optimization gives better full duplex behavior. So I'm sorry. Yeah, this curve. So this upper one is optimizing both the antenna ratio and the self-interference cancellation. If we didn't consider the self-interference cancellation in the optimization, the performance would be less, and this one will be this optimization.
So Hirat, what I have a question.
Yeah. Okay.
So can you highlight, because I'm new in this domain, so I don't know when you present, I don't know what is your main contribution, because I am pretty new to this. So can you highlight a little bit your major contribution and any corresponding, any publication corresponding to the contribution?
Yeah, the list
like, do you and also like when you run the simulation, did you also compare against other approach in the literature? I mean, right here you say you compared different setting and duplex and so on, but do you compare against other approach trying to solve the same problem?
Yes, actually, the figures shown here, the dotted one was the dotted one, the pink one, the pink dotted one is actually a work that has been already done. It's not my work. So I have the results. They set alpha equals 0 and optimize the sum rate, and they found that the antenna ratio, the optimum antenna ratio, should be the number of downlink users over the uplink of the number of the uplink users. So in that case, I compared their work with the proposed work. So this is an example. So my contribution in this part, or in this dissertation, is to address the resource allocation problems in the combination of the full duplex, the massive MIMO, and the heterogeneous networks. So we consider different types of interference, and we set to the gain regions of the full duplex when it's better than the half duplex, the existing half duplex systems. Also, we propose some low complexity algorithms for solving these complex type of problems.
Mm-hmm. And do you have? So I saw you have some. Can I see the list of application?
Yeah, sure.
And corresponding to your contribution.
Okay, it will be much easier to go this way. Yeah, here is the list of applications.
And maybe by number 2, almost submitted. Because almost.
Yeah, to be submitted.
To me to be submitted. Because that 250 problem is here. you need to address it. Yeah.
Okay. Okay. Thank you.
Thank you, Doctor.
I have to say that this is more
So,
so the application in this area give you more connectivity. You have a kind of mass speaker for that. Yeah. Some of the data that review is longer than our paper.
I mean, first problem formulation falls into very classical maximum rate subject to power constraints formulation. And this body of literature is just huge.
Yeah, and people become.
So my question is not directly related to what you did, but the complementary formulation actually caught a lot of attention. Is for instance, either you could minimize the total power subject to rate constraint, or some people even do minimize energy per bit, and then subject to rate constraint. The reason they formulate that way is, of course, if you do fundamental limit or capacity bound, the formulation you did is fine. But if you talk about really the new system, especially 5G support, like real-time video streaming, this kind of applications, what the service provider worried about is actually quality of service, right? So how do they do it? Is basically for each app you run on smartphone or something like that. This kind of experiment done by a lot of companies, which is say, oh, if you want to do certain type of real-time video, the data rate has to be at minimum 240 kilobits per second. Below that, not possible. So that's why there are a lot of reasons that people do, like you have constraints which are agreed. Like minimum rate per user is more than a preset value, and then minimize or maximize battery life.
Yeah,
so I'm just wondering what kind of solution they will get compared to the fundamental limit you get. It could be quite different. I don't know, because I don't know anybody has done that yet.
Yeah, but another student. You see this question, right?
Yeah, because in the more traditional setting, not in the duplex or Python MIMO setting, the solution of the one I'm saying the QS-based formulation gives a very special water feeding solution compared to the traditional one.
And there's another reason for that. Okay, if you have the fancy QoS, something like that, it's harder to get this close form or this kind of symbolic behavior. Yeah, we have to kind of simplify this objective function, or maybe more classes, such as we can get to pretty fast. But on the other hand, okay, for some fancy kind of QoS, for the algorithm part, so we can use this kind of optimization part to achieve this part. And I have two more students, and maybe they can do it. They are not do asymptotic optimization. They do not do this analysis. They are pure algorithm. Then okay, this system works. Other question? Any question from the audience? Okay, according to the procedure, okay, maybe our committee will ask the candidate, so for the audience, do you want to stand up and try to attend this one? Not including that. No.
Overall, is it
Overall,
is really to decision right?
Do you need one more copy?
It's okay. And can you ask Dr. Hin? Hello?
Hi.
Hey, are you finishing your office hour?
It's until 2:30.
2:30. Okay, then you just stay there.
Maybe I can come quickly. I can maybe come quickly.
It's okay. It's okay. You just.
It is in the large conference room.
The large conference room.
Okay. I'll be there. Yeah.
Thank you.
We should follow the office hours strictly.
He's a professor.
Me too.
I don't even have an office hours.
You're a chair professor.
So okay, according to the procedure, any other questions? Beyond this.
I'm good.
Yeah. And I think the 251, and maybe we can discuss after this one. Okay. Yeah. And also, okay, allow me to advertise, and because he wants to, she's currently in Ghana, and there are some kind of small school around Ghana that we may have some kind of opening, and she wants to apply for the next year, and maybe okay, maybe she can ask for help with some of you.
Okay.
And, okay, so. Let's wait just 2 minutes until Dean comes here. And I have to ask him whether he has questions individually to you. And then after that, you help out. Hey, come in, please.
Yeah, I can open some.
So do you have other questions for candidate?
No, I'm good. And this is not my country, so I.
Then maybe you can
It's
start out.
Office hour too.
Yeah.
Okay. Is this the name right? Your name?
Yeah.
Okay, yeah, that's good. Okay. Okay, oh, by the way, Dr. Kiwi is our new hire.
How are you? Ben again. Nice to meet you.
Nice to meet you.
He's working on deep learning. We are working from overlap.
Oh. Excellent. So which part of deep learning do you think?
The deep part.
The very deep part.
Usually they call it the dark part. Because deep using too many times.
That's right.
So now they say the dark part. The dark part meaning you never see it, right? It's hidden from you.
Yeah, that's a point of the deep learning paper. You see the deep learning paper, and then in the middle they use TensorFlow. Then come on, a lot of people in my field use like that. Anyway,
Can I borrow that for a second?
sure. So any comments for this candidate? Anything or any?
Yeah, I mean that looks good. Except that she doesn't have many journals. So for our field,
I think
important.
my criteria is a 3. She has a 4. I think also, to be honest, this field is too
Crowded.
too classic. That's the point. Far too classic.
I remember back to 2012 when I'm looking for a job, a guy published how transactional information theory several transaction signal processing.
Wow.
go to North Dakota State University.
I know.
Got a season professor.
Wow.
So related to this.
Especially with if somebody in the deep learning with that complication, probably you can get
Exactly.
Probably won't go to school. Go to say
no,
Hawaii.
I mean, I think when it comes to, I'm not sure, but I mean, what I see is that I see some people going to good place because multiple factors, not just application, it's connection too.
Yeah, connection
and this is important in academia, right?
Yeah,
Area.
Area is
because I see a lot of people who don't have very strong publication go to very good place, and the other way around.
The thing I don't get, academic elder sister who is 9 months ahead of me. But at that time, the bubble is not clear. So nobody goes to the academic, and when he can easily go to where easy to go. But now, after that, every department has a communication guy.
Yeah.
So they don't
need.
But the timing is the most important.
That's true.
Or that for smart grade,
Yeah, need to say
I just write down
evaluation. You want this?
You can take a picture.
Oh, okay.
So this flag, your kind of flag? Blue, black.
This one?
Blackish. Not black.
Star. It's deep.
I teach reinforcement learning, and one of the examples go from industry, from unemployment to grad school to academia industry. So it's a micro decision process to go from.
How do you estimate?
If you are unemployed, then you go to grad school. After grad school, you either go to academia or industry. But there is no connection from previously they go without connection go from academia to industry. But right now there's a lot of academia go to industry, so we should add that into the decision process.
Do you know Ankit Patel at Rice?
Ankit Patel. I don't know him personally.
No, he just joined us a year and a half ago.
Okay. I saw his website.
Yeah, he's very good. You should get to know him. Because he's also very deep, dark person.
I saw his website. Yeah. So in Rice, like are you from East? Okay.
Yeah.
What's this?
Extra copy, I guess. Did I sign that?
No.
You cannot use it.
You all have to watch, not just some people. Everybody has to watch, right?
But I don't believe genetic, along genetic reason plays a big role.
Yeah, but still, even
I need to before that guy died.
enjoy that.
That's the spirit.
It not be like that.
So although I happen to lead the deep learning team in Uber, but I don't sell myself as deep learning guy. It's actually if I go everywhere, I would sell myself as a medical, like the machine learning in medical. And I think that would be, and that is already my main topic. This deep learning is actually a tool.
And you use it anywhere.
Yeah,
Really.
I use this everywhere, but I think in medical there's another challenge where, for example, genetic, machine learning for genetic, and for many things, it involves small number of training samples. And of course, I mean, we can use deep learning, leverage unsupervised data, and so on, but there's still a very big gap between, how deep network do and how the traditional human do learning. So I think that is still a missing gap. And there's, and also I mean, in the medical domain, when a doctor makes a decision, he or she will based on a very broad, ad hoc knowledge. It's not like, okay, I'm gonna combine systematically the Bayesian framework maybe, but they use heuristic reasoning a lot, and that is not there.
Yeah, she's probably nervous now. Why is it taking so long?
She's very nervous.
Tell her they prepared too good.
Yeah.
So every new field, then your department will open a new position in that way, or how does it work?
It all depends, it all depends on this. Because that is very nice thing. It all depends, it's sometimes sometimes just what the faculty wants.
Yes. Okay.
You don't want to chase every hot topic.
Right.
You want to chase some hot topic.
But if you check the market this year, it's all different. Machine learning.
Yeah.
Data science. Big data.
Time to move.
Yeah.
Just kidding.
I have this 40% of my energy is my identity. So because I have to accumulate over the long time, okay, the people really they give me the kind of identity. And 60% try to withdraw whatever the hot is.
That's good.
My current student working on security start to worry about the future job. I convert some of them of security plus deep learning to guarantee in the future they can find a job somewhere.
Yeah.
But in fact, if you really look at the job market prediction, the cybersecurity part, the workforce need much higher than others.
I mean, during the last 10 years, I saw a lot of positions in exam about cybersecurity. But this year, if you check the market, it started to decrease.
You're talking about cyber.
Yeah.
That's the difference.
Yeah. Industry.
Sure. Now everybody speaking? Yeah.
Thank you.
Take your time. Or everything's okay? Yeah. Do you want to go back to running or want to stay?
No, I go home.
Okay.
For Iceland.
Oh yeah.
Picture.
Picture time. Can also use my phone. Yeah, let's have a. Can you go to the first page? Yeah. Okay. Let's go.
Tell me where to look.
There are many pictures. I think the size is fine.
Multitasking.
Okay, great. Okay, great. Thank you.
Nice meeting you.
Nice meeting you too.
again.
We see you around. Yeah. You should come to Rice and give a talk on
I did come.
Oh,
I have a friend there.
Oh, okay.
Ashok.
Ashok, you're another one?
Yeah.
You know him too, right?
Same university, same advisor.
And I also, I think we also graduated from the same university.
Yeah. You work for Ramsey.
Yeah.
Okay. That's why you look familiar. You must have come to Duncan Hall to give a talk.
I didn't. I came several times, but didn't give a talk. But I, in the past, I worked in some Java projects with Richard Barrymore.
Okay. Now,
Because more.
Absolutely. Congratulations.
Thank you.
Sure. Bye, everybody. Bye. Bye.
Well, my work.